today I'm going to be going through, as I said before, some of the latest and greatest in what Mitsubishi has to offer. And ultimately, this is continuing our conversation about strategic electrification and what manufacturers in general are doing in order to answer some of the questions and demands of the market. We've been hearing a lot of people, they want to move towards removing refrigerant or reducing the amount of refrigerant in occupied spaces. So some of the different methods that we're going to be talking about tonight either drastically reduce or outright eliminate refrigerant in occupied spaces. So again, some of these we're going to be going through products that have not yet launched in America, but others as well are current products. So I'm going to be giving a breakdown of each. Okay. All right, so just going through this presentation, I'm just going to first start with a quick overview of VRF systems as a whole, just to make sure everyone is on the same page in terms of the components that make up the system. Then I'm going to be talking about the HEX or heat exchanger indoor units, HEX fan coils, which are essentially the refrigerant-to-water heat exchanger units that are a current product in our product lineup. Then we're going to be talking about HVRF or hybrid VRF, which is kind of a combination of those HEX unit fan coils with existing heat recovery systems. This is, as we are looking at it, the next generation of VRF that is going to eliminate refrigerant in occupied spaces. And lastly, we're going to give a quick overview of one of the products in the pipeline, the QAHV domestic hot water heat pump system. So that product in particular, where we're currently looking at a Q4 2021 launch. So the data I have in this presentation is likely the majority of the information I have available. So any questions on that topic, and I know it'll certainly cause a lot of interest. I'll have to table quite a few of them, have to circle back with our applications group, but ultimately, if you have a question, I'll make sure to get an answer to you. All right, so we're just going to start with a quick overview of VRF and the components that make up a VRF system. So when we're talking about a VRF system, we're talking about one of two different subfamilies. We have our heat pump family of equipment, which is shown schematically here. We have 9 different fan coils, all attached to one single refrigerant network. And for this particular configuration, all of the fan coils that are on this one system, they are either going to be in heating mode or cooling mode. So with this particular system, you're not going to get simultaneous heating and cooling throughout. That's going to require an additional component. So just laying out the components of the system very simply, we have our condensing unit outside, your indoor units, your fan coils, and the control system connecting the entire system and being the brains of the operation. And graphically speaking here, just showing the difference between these. So a little bit, we have our cassettes as our fan coils, our wall-mounted equipment. We're all familiar with these particular families. Now, with that said, as opposed to heat pumps, we also have our heat recovery series of equipment. Now, heat recovery, this is where you are going to get the capability for simultaneous heating and cooling on one single refrigerant network. And the difference that we're looking at here is the introduction of this additional component right here. I'm circling with my cursor, central to the system. That's what's referred to as the branch circuit controller. So going back to my little button overview here, the branch circuit controller, and shown graphically here, is we're going to have 2 pipes of a refrigerant network connecting our outdoor units to our branch circuit controller. And then the heat exchange process occurs within the BC controller itself. And then each fan coil or group of fan coils that are connected downstream of the branch circuit controller, every port is individually going to be supplying heating or cooling as is requested by the zone. So ultimately, that was just a quick overview of what VRF systems are and a top-level overview of the difference between our heat pump and our heat recovery systems. Now, building off of this, the first topic we're going to be talking about today is our HEX unit fan coils. HEX, HEX, or heat exchanger units. These are our refrigerant-to-water heat exchangers. Ultimately, the HEX units, the VRF system itself, it's going to see these as just another fan coil on the system. So to the VRF system, it's the same thing as a wall-mounted unit, same thing as a cassette. It's just its own individual fan coil. So I'm just going to move on to this topic. So HEX fan coils. Here are a couple pictures that just demonstrate what we're talking about when we're looking at a HEX. On the left is just an overview of the product itself, and the right, this is actually, we have installed at one of our training centers with a plexiglass covering so you'd be able to see the inner workings of the unit itself. And actually for this picture on the right, this is going to be our HEX booster unit, and you can tell that by the compressor that's in the lower left corner right here. So the HEX booster unit, as opposed to the standard series, is what enables this particular system to boost water even higher because it has its water temperatures even higher because it has its own separate independent compressor refrigerant circuit.
Mike, can I jump in and ask a question here?
Sure thing.
Yeah. You had referred to the HEX as a fan coil unit, but it doesn't have a fan. It's an indoor unit, right?
Correct. Yeah, and forget the confusion there. I'm just going with the terminology of indoor unit, fan coil. I use those interchangeably, but you're exactly right. There is no fan in this unit. It is more appropriately called an indoor unit.
Okay.
All right. So, and when we're talking about our HEX indoor units, we're going to be talking about one of two different series. We have our HEX auxiliary units, which are capable of heating water to 113 degrees, and the booster units, which can boost even higher with that independent compressor up to 160 degrees. Now, both the HEX and the booster unit are designed for closed-loop heat exchange applications. Now, connections to any other open-loop systems, such as domestic water, that needs to be handled via a secondary heat exchanger. So we can't just independently have fresh water, fresh potable water go through these and expect to be able to drink the water. These are for closed loop systems only. Now, the closed loop system serving the HEX or the booster unit should also be chemically treated with corrosion, rust inhibitors, a balanced pH. Ultimately, we want to make sure that the water that's running through these, it's not going to eat away at the pipes themselves. We're going to have healthy water in here. And especially in this particular climate, we're going to want to make sure that we have glycol for freeze protection down to at least -4 degrees. Now, and also, since these units are intended for closed loop applications, we're going to be need to apply circulation pumps in order to circulate the closed loop heat exchange fluid, water in this case, through the unit. And during the design process, we're going to want to make sure that pressure drops and flow rates and all the equipment this is going to be going through, all the parts, that's taken into consideration in the design process. So just going to give a quick break. Oh, sir?
Talk about the actual cooling on that. How does that actually cool? You have the HEX unit and the HEX booster unit. So
Yep.
do heating and cooling?
That's a good question. Yeah. So the only one of the two units, the auxiliary unit, is going to be capable of cooling. And I'm just going to move on to the next slide because you got 1 second ahead of me there, Wes. So the auxiliary unit, this is going to be able to have various modes of operation in heating mode. Obviously, just standard heating, we're going to have a full temperature range available. Heating eco-friendly mode, that's going to adjust the supply temperature based on the outdoor ambient conditions, as well as antifreeze mode, which is just going to circulate that water to make sure we're not going to be freezing up in the pipes. Now, with that said, we also have a reversing valve built into the auxiliary unit. Kind of same situation with like a heat pump system in and of itself, where we just reverse the cycle and put out cooling rather than heating. So we're going to be removing the heat from the water as opposed to adding. So in cooling mode, this is going to be able to provide cool water from 41 to 86 degrees. So again, the cooling mode, that's only going to be available in the HEX auxiliary unit. And for the aux units, these are going to be available in 3 and 6 tons. Excuse me. Just take a quick water. Sorry about that. I had a little seed caught in my throat from a bagel I had before. So, yeah, the aux unit, that's going to be in 3 and 6 tons of nominal capacity. And just to reiterate, these units aren't potable rated, closed loop systems only. They're not going to be able to provide the potable water just with themselves. And just to give an idea of the size of the equipment we're talking about, is just to provide a dimensional diagram. Again, it's going to be 1 foot wide, 18 inches deep, and 31 inches tall. For the aux unit, this is going to be around 80 pounds, as opposed to the booster unit. That's going to be adding a little bit more because of the additional compressor. Now, I also have here, I have drawn up a schematic for how exactly a HEX unit would play into a VRF system. So for this particular layout, I'm just going to start my way for the outdoor unit and work my way in. So this looks like a typical heat recovery VRF system. We have the outdoor unit, which is going to be an R2 series, connected to a BC controller, 2 pipes going in. The BC controller, we have 2 cassettes attached to this. So we have each cassette is in its own independent mode. So one of these cassettes is going to be heating, the other in cooling. But in addition, we're also going to have this water HEX unit. And again, the HEX is just registered on the system as just another indoor unit. So no additional programming needs to be taken into account. Once it's plugged in, the system knows what it's looking at here. It's just another fan coil, for lack of a better term, or another indoor unit on the system as a whole. So the HEX unit in this instance, as we're working our way in downstream from the port of the BC controller, the refrigerant that's going in is going to go through the linear expansion valve, or the LEV, within the HEX unit. The same LEV that's going to be in every single indoor unit, like cassette unit, wall mount. But that's quite simply, that heat exchange process, we're going to go through a plate heat exchanger within the HEX unit in order to transfer the heat, refrigerant to water, or vice versa, or removing the heat from the water if we're in cooling mode. So in this particular schematic, we have a closed loop circuit, secondary loop, and this is just demonstrating that we could go through a floor heating system, panel heater, or a fan coil itself, an actual air handler with its own hydronic coil built in. And I have a couple pictures here from an installation where we've actually had these HEX units installed. This is located in the Lexington, Massachusetts fire station. So on the left, we actually can see some of the branch circuit controllers above that are going to be ultimately feeding down the refrigerant to these individual units. On the right, we're seeing 1, 2, 3, 4, 5, 6, up to 10. So in this particular instance, we have 10 zones of essentially hydronic loops. So these are all HEX aux units, so they're going to be able to provide heating or cooling to whichever water loop that's going to be connected. In this particular instance, this water is used as a hydronic loop throughout the station, and it's able to provide heating and cooling to the space. So this is just an application of how we can see a refrigerant to water heat exchanger essentially bridging the gap between a hydronic loop, an existing hydronic loop in a building, with a high efficient heat pump system with a VRF system.
Mike, what sizes do they come in, and can they be daisy chained together?
Can you ask that one more time?
Yeah, no problem. What sizes do those HEX units come in, and then can they be coupled together?
Yes. So for this particular instance, this is 3 or 6 tons for the aux units, and the aux units are those that could provide cooling. Whether or not you could twin them together, it's actually a good question. I want to verify that. I myself, in instances I've worked with, we've had independent loops, but I'm just going to take that down. And you're asking if we had potentially needed 12 tons of heating and cooling on a loop, if we could put 2 6-ton units twin together on that?
Correct.
Yeah, so I just want to verify that. I haven't seen that done, but I'm sure that's somewhere buried in this 30-page application that I have in front of me. So I'll just get back to you on that after the presentation.
Mike, it looks like you have, after these heat exchangers, can I call them just heat exchange units? Is there a
Sure.
refrigerant-to-water heat exchange? So then downstream of that, you just have a two-pipe system. And that, what I'm seeing here, what's nice is that you have branches of a two-pipe system, and you have a shared plant, but you're not tying everybody together because the branch controller and the heat exchange function of the branch controller. The building can be in multiple modes at once. It can be heating over one side, cooling on the other. It's not locked together to one central plant.
That's correct. I'm sorry, was there a question to that?
Let me come up with one. Could you tie into an existing two-pipe system?
Yes. Yes, you can. So this is something that we're actually in the process of working with a system over in Attleboro specifically. We have, I'm sure you actually know exactly which system I'm talking about. We have an existing,
some of us do.
Yeah, some of us do. We have an existing chilled water fan coils in a space. They're on an existing water loop, so we're looking to potentially retrofit and reuse some of the vertical stack fan coils that, or potentially reuse the enclosures that exist today, potentially with new vertical stack fan coils, with the HEX units themselves providing the either hot or chilled water that's going to be ultimately running through these coils. So that's a potential application that we're looking at as a way to broaden the applicability of the HEX fan coils. And I'm sorry if I keep on saying fan coils over and over again. That's just, it's like Kleenex versus tissue. I'm just used to saying that. Indoor units is certainly more appropriate.
And you had mentioned also that these, you want them set up with a 26-gallon or so buffer tank. Is that a tank, or is that you want the loop to have at least that much volume?
Yeah, we're going to want the loop to specifically be in a tank. And ultimately, that's going to be, so we want to make sure that we have enough hot water available for an entire defrost cycle. So that 26-gallon tank, that's size for the flow rate of these units, multiplied by the 10 minutes, or 10 to 12 minute defrost cycle. So that way we're not going to be coming on the tail end of it, and the water that's potentially sitting in the pipes is slowly cooling down to the point may not be able to keep up with the heating demand of anything downstream. So those buffer tanks are specifically there to account for the defrost cycle. Okay, so I'm just going to move forward. So separate from the aux units, those are units with heating and cooling capability, we also have our HEX booster unit. Now, the booster unit is similar to the aux unit, still acting as a heat exchange device between the VRF's R410A refrigerant loop and a water loop. However, the booster unit also contains a secondary R134A refrigerant loop within itself that has a secondary compressor that allows the unit to produce even warmer water. So in this particular unit, you have a hot water mode in addition to the heating mode, which boosts the water temperatures up to 160 degrees. Now, the booster unit, unlike the HEX auxiliary unit, cannot provide cooling for the water loop that it's connected to, since the 134A loop that's within it does not contain a reversing valve. So we don't need to worry about that application with the aux unit. In the booster unit itself, there is no reversing valve to allow for a cooling process. Now, that said, as with the HEX auxiliary unit, this can be connected onto any VRF system or any three-phase city multi-VRF system with other fan coils. And the only limiting factor on this is just connection ratios. And ultimately, that's going to be, we're going to work with any customer looking to design this process, work very closely to make sure that everything's designed properly, everything's sized accordingly, etc. That said, the booster unit, only one size available for the booster. That's only going to be 3 tons of nominal heating capacity, as opposed to 3 and 6 tons available for the aux unit. And similar dimensional diagram just to showcase the same exterior dimensions as the aux unit. It just has that compressor built in that's going to bump up its net weight to about just over 130 pounds. All right, so this particular schematic, we're similar to what we were looking at before, except for this unit, we're going to be utilizing a HEX booster unit in order to boost the water temperatures to hot water temp. It's going to be in hot water mode up to 160 degrees in order to provide preheating to a domestic hot water storage tank. So in this particular configuration, again, as we could say, the water loop running through this particular tank, this is a closed loop. So this isn't going to be introducing any hot water to the tank itself. It's just going to be running through and heating the water within the tank. And this application we could use to ultimately reduce the peak load on the domestic hot water heating system. So if there's an existing fossil fuel driven domestic hot water system, this particular schematic and this sequence we can use to ultimately reduce the peak load and ultimately pull down the carbon footprint of that particular building. And this slide I put together just to showcase the fact that the HEX unit, it doesn't ship completely ready. There are additional components that we need to factor in. We need to have a vent, a flow switch, pressure temperature ports on the inlet and outlet, balancing valves, shut-off valves, and a strainer as well. No need to go through and memorize all this equipment. Just letting you know that in designing these systems, there are some external parts that we're going to be also putting onto the system. Some of these I need to familiarize myself with. This is kind of my first foray into plumbing engineering as a whole. So some of these components, especially with the QAHV, the domestic hot water heating, I'm personally getting familiarized with myself. So, all right, in terms of potential applications for a HEX system. So right off the bat, one potential application is a radiant floor heating loop or a snow melt loop, something that could be popular in the Northeast. Now, the water temperatures in the HEX, they're capable of being heated within the range of supplemental heat for in-floor radiant heating, as well as snow melt loops. Now, we should consider whether or not this will be done in tandem with an existing or a third-party fossil fuel-driven boiler, or it could potentially be done without it and be entirely electric-driven. So, for this particular schematic, we're looking at a snow melt loop that is entirely driven by an electric heat pump system. So for this particular scenario, just going in, we have the HEX unit in the bottom left here. That's going to be serving the hot water to a buffer tank. That's going to be sized for that defrost loop. Again, the minimum size is the GPM rating of the HEX unit by 12 being the total minutes for defrost cycle. And downstream of this, we're just going to be delivering that hot water to a zone header and out to a snow melt loop. Ultimately, pretty straightforward. Other options, potentially, we have the potential tying into a domestic hot water system for preheating. So we want to make sure that we're factoring in peak domestic hot water draw when focusing on an application like this. And considering the peak domestic hot water draw, the selection of the primary domestic hot water system can ultimately be determined. Typically, the capacity of the hot water heater could be adjusted based on the amount of hot water storage used in conjunction with the peak heating rate of the domestic hot water heater. All that said, we're trying to ultimately draw down the amount of gas that we're going to be using to burn in order to create this hot water. So in this particular example, it's going to be supplemental heat in order to pull down the peak heating draw for the domestic hot water system. And lastly, here's an example for tying the HEX unit with a DOAS system or an air handler unit with a hydronic coil. So since the HEX units are connectable with City Multi equipment, we could get extended heat pump range with your VRF indoor units, as well as providing a DOAS unit coupled to potentially a hyperheat product or a low ambient heating product. So you've now tackled both your comfort heating and cooling and your ventilation demands, and designing around it with the pretty extreme colds that we see in the Northeast environment. So ultimately, we just need to make sure that the hydronic air handler that's provided by others we're going to be sizing the coil appropriately. We're going to be sizing the HEX units that are delivering the water to that appropriately. And certainly we're going to want to make sure that we're going to have a glycol for freeze protection, since this is 100% outside air application, and the fact that most likely we're going to be running the water piping outdoors as well. And additionally, we could also couple a DOAS unit with an ERV for heat recovery to minimize the need for aux supplemental heat. So again, these are just ways that we're driving down the amount of fossil fuels, driving down the carbon footprint on a particular HVAC system by bringing as much as possible onto an electric heat pump product. All right, so with all that said, everything that we've discussed thus far is currently available in Mitsubishi's lineup. Moving forward, the HVRF or hybrid VRF, this is the next generation. We currently have one install that is up and running at Berklee College of Music in Boston. We're currently coordinating with the school in order to develop schedules for taking customers to go through, see the system in person. But just wanted to give that disclaimer. So this is a coming soon product. It's in the moment we're going through UL testing, going through AHRI testing before everything is certified. But when we're talking about HVRF, we're ultimately talking about a combination of the HEX unit that we just went through and the standard heat recovery system. So just jumping back to the components that make up a heat recovery system, and the thing that makes the heat recovery system capable of simultaneous heating and cooling is that branch circuit controller, that middle component that's central in the system. So again, schematically, we're talking about the branch circuit controller here in the middle. Now, the HEX units, as we talked about before, they're just seen in the system as indoor units. It's just another indoor unit in the system. So what hybrid VRF does is it incorporates a HEX unit into each individual port of the branch circuit controller. So introducing hybrid VRF. So what we're looking at here in this schematic, we have the condensed unit outdoors, serving refrigerant piping to the hybrid BC or HBC controller. So we're going to be having two pipes of refrigerant piping leading from the outdoor unit to the branch circuit controller, and that's it for refrigerant. In terms of R410A refrigerant, that's all that we're going to be seeing in the system. Everything downstream of the hybrid BC controller is going to be water piping. So when I said that the HEX unit is essentially built into each individual port, obviously it's not a whole HEX unit. Those are a little bit beefy, but it's the components that make up a refrigerant-to-water heat exchanger in each individual port for the HBC controller. So we can provide water piping downstream and provide simultaneous heating and cooling for each fan coil in the system. So just a top-down layout of what we're looking at here, just to drive home the point of how much we're going to be removing refrigerant from the system. On the bottom right, we have the condensed unit outdoors and serving refrigerant piping indoors to the hybrid BC controller that's in this closet. And that's all we need to account for with ASHRAE 15, ASHRAE 34, refrigerant concentration limits. We don't need to worry about any refrigerant running through occupied spaces, running through apartment units, condos, anything of that nature, anywhere anyone's going to be sleeping. I know it's it's an item of concern that I've heard come up, that we don't want refrigerant piping in a space where someone's sleeping for one reason or another. Whether how conservative you are in your designs, you want to remove the refrigerant from that space. This is how we could potentially accomplish that. So this picture is actually from that the Berklee College of Music install site. So this was before they covered up any of the actual piping. So I thought it was a great visual just to see exactly what's going on here. All of this piping that you're seeing is all water piping. There's 2 pipes. Obviously, we have the 2 pipes of refrigerant going to the condenser unit. On this particular instance, I think it's just out of view of the camera. But this is what you're going to be seeing in the space. Anyone who is interested in going to the Berklee College for a site visit, what's great is that while the pipe itself has been encased in PVC, everything is still exposed, so you're able to walk through the entire system just looking at the ceiling. All right.
Yeah. A BTU meter on that. Is that
I'm sorry?
at Berklee? There's a BTU meter, it looks like, on that pipe work. The 2 straight pipes are coming out. A BTU meter on the right-hand side, the temperature probe back on the other side. Is that Berklee
correct.
are doing themselves, or is that something that's to do with the system?
That's the brainchild of Matt Berry, who is the commercial manager for Mitsubishi Electric. Those BTU meters were put into the system as a way of drawing up a very comprehensive overview of ultimately for a very in-depth case study of HVRF in an American installation. We currently don't have a case study on HVRF outside of an older European model that we can't quite apply like for like. So in installing this throughout the entire system over at Berklee College, we're going to be able to draw a lot of data and have very comprehensive analysis on the cost savings to the space.
Sounds good.
Alrighty, so in terms of key drivers, and forgive me if I'm reading off the slide a little bit, some of this was taken directly from the HVRF European presentation. So we haven't developed a full American Prezzo on this equipment yet, just because it's still ramping up in the market. But obviously, one of the key drivers is no refrigerant occupied spaces. This has been a concern that we've been hearing, so this is a solution to that concern. So any of the spaces, we're going to be just running water through the spaces. We're going to be having the benefits of a chiller system, very, very comfortable cooling benefits. Super quiet operation. I know VRF is known for its super quiet operation, but again, now we're removing even the sound of the clicking of the valve, so you may get that if you're super anal about, I want this to be the most quiet system possible, maybe the clicking of the valve be a bit too much for you. This is even more quiet. So we're going to be getting similar decibel levels to water fan coil units. We're looking at PEX piping, plastic piping for an install, as opposed to copper piping throughout the system. So we're going to be looking at significantly reduced install costs from a material standpoint, as well as from a labor standpoint, because we're not going to need to braze any of the connections since it's all plastic piping. Obviously, GWP, we're going to be reducing it by reducing the amount of refrigerant in the system. Even if it's a low GWP refrigerant, it still has global warming potential unless you're looking at a refrigerant like CO2 or another natural refrigerant. So we're ultimately reducing the amount in an individual system. And lastly, and this can't be understated, the uncertainty of the future of the refrigerant market. We are all collectively benefiting from the fact that the VRF market is standardized around an R410A refrigerant for this particular generation. But over the next few years, no one can really say definitively what direction all manufacturers or individual manufacturers are going to go. I mean, I could provide some insight to where Mitsubishi is looking, but again, that every 6 months I hear an update that could potentially change that. So, we're not even certain we're standardizing around any individual refrigerant moving forward. I don't know if it's going to be R32, a blend of some sort, or if we're ultimately going to be, everyone goes in different directions. But the fact that we're drastically reducing the amount of refrigerant in the system, we are going to be avoiding circumstances such as existing R22 systems that cost an arm and a leg in order to service them, in order to top them off with additional refrigerant. So even in the event that the R410A refrigerant slowly gets phased out, we're not going to be needing nearly as much in the system as a whole for an HVRF system. And again, for the design install, we're going to be using PEX water piping. A lot easier to isolate these. This is just water, so we could just turn a valve. Actually, I'm going to run back to the picture here of the install. The joke I was making when I was on site is that if any of the kids in the dorm rooms just wanted to prank the people next door, they could just go out to the hallway and just shut off the valve, and you're not going to destroy the entire system. You're just stopping water flow to your unit. So in the middle of the summer, it'd be an interesting way to mess with everyone that's making you upset, keeping you up late at night. But water pipe, it's easy to isolate, easy to reroute if necessary. If we have a leak in it and ultimately we want to remove it from a particular hallway, it's water piping. No need to pump down an entire system or pump down everything downstream. It's just water, easy to work with. Brazing process, as previously stated, no brazing downstream of the BC controller. The actual defrost process is going to be quicker and more efficient than for just a standard VRF heat recovery system. The fact that we're utilizing water, the actual fan coils themselves are going to be seeing a sensible heating capacity improvements. So we're going to be seeing up to 10% of an improvement in sensible heating capacities. And of course, intuitive load adjustment, ultimately it's a VRF system. So we're going to be having intelligently driven compressors, inverter driven compressors that are going to be providing the most efficient heat pump heating and cooling to the system. From a service and maintenance standpoint, as previously said, future-proof, so we're limiting the amount of refrigerant in the system, so we're limiting the headaches involved of acquiring more refrigerant in the system, potentially having leaks downstream of the BC controller. A leak downstream of the BC controller at this point is just going to be a water leak, which isn't great, but you don't have the complicated process of brazing pipes together that potentially could be prone to leaking. You have, a qualified installer, a strong installer, you're not going to really be looking at any of those types of leaks. And here's something interesting. All the maintenance in the system is handled at the HBC controller itself. Valves, pumps, heat exchangers, everything. We don't need to potentially go into a tenant's apartment in order to service their equipment. There's no expansion valves in the actual fan coils on these systems. Everything is located in the HBC controller itself. So if we go back to that schematic previously with the HBC in the closet, that's just where your service guy needs to go. He doesn't need to bother anyone, knock on doors, or get permission to go anywhere. Everything's just handled at the HBC. Again, we're going to be wanting corrosion inhibitors in the pipes. We're not going to want to see the pipes just slowly degrade over time. Plastic piping, easy push fits. We're reducing refrigerant volumes up to 38%. So all that just from a service and maintenance standpoint, we're seeing a lot of improvements. And some of the major questions we see about the future developments of VRF in order to make it easier on the installer, easier on the service guys. One thing I hear time and again, and I could argue it to death, but I get a question. I get comments all the time. Yeah, they're leaky systems. VRF is leaky systems. And I ask, okay, where's it leaking? Is it leaking in the condenser unit? No. Is it leaking in the fan coil? No. I'm like, okay, well, in the system as a whole, I mean, I don't know what to tell you as the manufacturer, but there's only so many times you could say that before someone just says, well, they're prone to leaks, so ultimately maybe we should go with a different system. So that's a valid concern. So we're reducing the amount of potential for refrigerant leaks and ultimately eliminating that particular problem. All right. So in addition, I'm just going to walk through the flexibility of this design. So HVRF actually introduces the ability to do some pretty interesting things in terms of expanding the system. So for this particular look, this is very similar to a standard heat recovery system. Just, you know, 2 pipes into the BC and then 2 pipes to each fan coil. It's just in this particular layout, this is going to be water downstream. Similar look to a standard heat recovery system, adding a sub HBC controller. So a sub BC or an expansion controller. Except one thing of note, we're going to have 4 pipes of connection between these two units. And this is going to be water piping, not refrigerant piping connecting the main and the sub HBCs. And it's 4 pipe at that point because we're essentially going to be acting as a 4-pipe chiller, simultaneous heating and cooling chiller between the main and the sub HBC. Now here's where the really interesting thing comes in. What is new with the hybrid VRF system is the ability to have a second main hybrid main BC controller. So forgive me if I'm saying hybrid BC or HBC or BC controller. Ultimately, I'm talking about the same thing here. So the difference between a secondary main HBC and a sub BC controller, that's just like an expansion, is that the main BC essentially operates as its own individual datum point when we're talking about line lengths for a system. So one of the limiting factors for the size of a VRF system is how far away the furthest fan coil is allowed to be from your BC controller. Well, for this particular instance, having a second main BC on a system, we don't need to worry about the distance from the primary or the first HBC. We can use the secondary main BC as a new datum point to ultimately expand the distance that all the fan coils could be apart from each other. So just to go through what we're looking at here from a piping standpoint, as opposed to just a single main BC with 2 pipes going in, we're going to have splitting branch teeing off those refrigerant connections between leading to both the main and the secondary main HVC. And then this yellow line in between, this is just going to be water piping. That's going to be just balancing the water loops between the 2 systems. So again, for this, this is just an example of how robust and broad this particular install could be. Very flexible. We have 2 separate main HBCs, 1 sub attached to one of them. The second main BC, it can also have a sub. No need to draw down this particular instance, but this just showcases the flexibility of the design for this system. All right, so these slides I actually took directly from the European presentation. So some of these units are going to be in metric, so forgive me on that. But I'm just going to showcase how we can potentially get a further expansion and how we can have the fan coils even further apart from each other. So one of the pipe limits that we have to look at is that, you know, for this instance where the condensed unit is on the ground, we can have the HBC be 40 meters or less, so just about like 130 feet or so or less away from the condensed unit. We also have total line length 110 meters from the condensed unit. From your BC controller to your furthest fan coil, we're going to be looking at 60 meters or less. The height difference between HBC and your fan coils can be 15 meters or less. Between fan coils, 15 meters. Again, all this is just numbers at this point, but this is where I want to really drive it. The max height between these HBC controllers. So we can have up to about 45, 50 feet between these HBC controllers. So if you're running into a circumstance where the vertical separation of your fan coils on a heat recovery system, it gets too great, you're exceeding the limits, well, that pretty much means that, oh, we can only have a maximum of 4 or 5, 6, however many floors on that particular system, whatever the line lengths you're going to be encountering. By having these two main HVC controllers able to be offset from each other, and all the fan coils attached to each main BC will only be relative to their parent, we're able to get further distances away from each other from fan coil to fan coil. All right, so ultimately that's what I wanted to demonstrate. All right, any questions on that? So pipe limits and elevation limits for this? I know this slide could be a bit heady, so let me know if I've lost anyone.
Do you have different types of indoor units that you're discussing about on this presentation?
Yes, so for initial launch for the HVRF system, when it's first coming out in the US, we're only going to be talking about our concealed ducted units. So so in this particular circumstance, we're looking at cassettes attached. Those are going to be a future allowment, but for the time being, we're only going to be talking about these ducted units right here that are going to be attached. And that's because we need to rework the actual fan coils themselves. Again, we're not going to have any of the valves in the actual fan coils themselves, so we need to rework the interior of each. So for the time being, we're only going to be looking at the medium static pressure concealed ducted units. Right. All right. As a demonstration, this is a slide we often see that just differentiates Mitsubishi or any two-pipe heat recovery manufacturer from three-pipe heat recovery manufacturers. I'm not using this time to either say one way or the other in terms of whether two-pipe is better or three-pipe is better. Me personally, I've worked for manufacturers that did both. So there are certainly advantages to both methods, but ultimately I'm trying to draw the corollary between the two-pipe a city multi Mitsubishi VRF and HVRF, and how we're totally how we're ultimately to be reducing those refrigerants. I'm getting a little bit of feedback. I don't know who has themselves unmuted, but if we could just mute, that'd be cool.
I just took care of that.
All right, perfect. All right, so in this instance, we're just demonstrating that for a two-pipe system, since obviously we only have two pipes of connection between the outdoor unit and indoor unit, we're only looking at 4 connection points between those two. We're also going to have brazing downstream between the BC controller and any fan coil. Again, this is just for a traditional VRF system. For a 3-pipe system, again, everywhere you have a connection, you're going to have brazing. So ultimately, this is a demonstration for this particular layout. You're going to have substantially more connections, many more braze points. Now, I'm going to contrast that with a standard VRF and an HVRF system. So both of these Mitsubishi equipment. So for this particular, on the top layout, where it's just a standard heat recovery system, 4 fan coils, we're looking at 20 different braze points. It's 2 connections at the condenser unit, 2 connections at the BC, and 2 connections for each port and each fan coil. That adds up. But ultimately, you're going to be reducing that. Everything downstream of the HBC controller is going to be water piping. The only braze points are between condenser unit and the HBC controller. Just want to use a slide to demonstrate that the controls layout for the HVRF system, it's the same exact controls layout as it would be for a standard city multi-VRF system. Everything is single point controlled, single point transmission wire from unit to unit, daisy chained. So ultimately, it's going to be the same MNet or Mitsubishi network for the VRF system.
Mike, what would be the difference between the controls on that versus the HEX system?
Yes. So, well, again, the HEX unit, that's just registered on the City Multi VRF system as another indoor unit. So when you connect the communication wire from the main BC to the HEX unit, it's going to be the same exact connection you see here between this BC and this fan coil. It's just single point connection. Obviously, there are hardwired points on the HEX unit as well for a little more customized control. We can have water loop temperature adjustments based on a based on an analog electrical signal output to the HEX unit. But yeah, again, the HEX unit is just single point communication wiring daisy chain throughout the system.
Okay.
All right, so this is just going to go through some of the components that need to be installed on the HVRF system. Again, we have water loops, so there are going to be some additional components that aren't on a traditional VRF. So we're going to need an expansion tank at each HBC controller. We have a filling loop, Cat 3, Cat 4, strainer on each HBC controller. Pressure reducing valve, isolation valves, again, and that's going to be for all branches as well as pressure gauges. Again, the more of these we can get onto the system, the better, but ultimately, off of the main water supply, we're going to be wanting these particular components. And again, just to highlight the fact that any sub HBC controller, it's going to be four pipes of water piping, 2 hot and 2 cold water feeds. All right, so these pictures, they're that same installation site, the Berkeley College of Music. So this is after we encased all the water piping in PVC. So this is ultimately what the final install is going to be looking like. All right, domestic hot water. I imagine we're going to be getting a lot of questions here, so you certainly have to bear with me. So what I have in the presentation is the bulk of the information I have offhand. That said, any questions you have, feel free to ask away. I could just shoot on a list down to our engineering group and see what information I could get. All right, so when we're talking about domestic hot water heat pumps, I want to differentiate the options we're talking about here. So the lineup we're looking at the screen, this is the current European market lineup for hot water heat pumps. The 2 units that are on the right and the green, those are capable of both domestic hot water heating as well as standard heating like VRF, comfort heating and cooling. That equipment is to be determined when we're going to be seeing it in the United States. So for the time being, we're only going to be focusing on the QAHV equipment, which is just solely a domestic hot water heat pump. There's not going to be a separate comfort heating loops off of this. So just to give you an idea, this is a self-contained unit. This is only going to have water connections coming out. All the refrigerant within the system itself is located entirely within the condensing unit. And okay, so with that said, I just want to point attention to the heating capacities we're looking at here. Per module, each one of these units is going to be capable of just about 10 tons of heating capacity, 136,000 BTUs of heating. And we can actually connect up to 16 of these modules together for up to 2.2 million BTUs of heating capacity. So for the QAHV, the way we're going to be accomplishing this, substantially high heat output is by using a high pressure refrigerant in CO2. So CO2 refrigerant, from my previous life when I was working in commercial refrigeration, we often saw CO2 in critical low temperature applications where we needed to maintain spaces close to 0 or well below 0 in freezer farms or things of that nature for large, 100, 200 ton types of systems. So we're bringing that CO2 technology into a commercial 3-phase hot water heat pump system. And by utilizing CO2, we're able to get ultra high efficiency even at cold temperatures. So we're looking at just under a 4 in terms of the COP. And I believe I have those charts. Oh, that's right. So I'm waiting on the D-rate charts to actually showcase how the COP is affected in low ambient conditions. But with that said, this particular unit can supply high temperature hot water up to 194 degrees. That is the European unit. we anticipate that when this goes through its certification and testing process in the United States, I'm unfamiliar with the guidelines for hot water equipment, but I believe ultimately that's going to be reduced down to about 185 degrees. But with that said, it's capable of producing hot water up to at least 194.
What happens to that temperature?
I'm sorry?
Mike, what happens to that temperature when it actually gets colder outside? I see here that it maintains 100% heating capacity at 26 degrees. Then it will operate down to minus 13. But what's going on with the temperature and capacity of that system at those temperatures?
That's a great question. For this, I have limited information about the D rates, but I'll go with the anecdote that we always talk about within Mitsubishi in its current installations in Europe. So there is one particular install that's in northern Scandinavia. My Scandinavian geography escapes me. I believe it's Norway, but regardless, it's a place that gets really, really cold. And at this particular installation, when it was below minus 20 degrees outside, just to test, they wanted to see how much hot water at what temperature they possibly could get. And they were still able to get scalding hot temperatures in their showers, even at even below minus 20 degrees. So, and one thing I do want to stress, these are low flow, high delta T units, and it's ultimately going to be tempering those tempering the water for storage tanks. So this is not an instant heating. It's not an on-demand heating. It's not going to be a direct heating of the water off of the street. It's going to be designed in such a way to heat the hot water and store the hot water as needed on a demand basis. So I'll go through the schematics, the different ways that we can control the hot water storage tanks, but that's ultimately the way we're going to be looking at it. But to your question as to the COPs and heating capacities in low ambient conditions, I don't quite have the info yet. I've been screaming for it, and as soon as I do get it, I promise that I'm going to be going on and on and on about it. All right, but as you said, these are rated 100% of heating capacity down to 26 degrees. If other city multi-equipment is to go off of, the D rates that start at that point are steady, and it's not an exponential decay. It's rather just a flat slope from 26 degrees down to the negative 13. So in Boston design conditions, I imagine that we'd be looking at, on design day, I'd be comfortable saying that I anticipate between 70 and 80% of your heating capacity in those temperatures. All right. So
is that where you have a backup heating on it?
I'm sorry, can you repeat that one more time?
Yeah, no problem. So you're saying here about the capacity being reduced. Would you have backup heating on these if the capacity is being reduced, or how would you take that into consideration?
So I don't want to answer that until I have a little bit more engineering data. The current engineering data book I have is dated 2015. And typically if I see that date on a data book, I'm thinking that, all right, a lot more testing has been done. I need more up-to-date info. But with that said, in terms of sizing for any backup heating, what you would need, it would all need to be comprehensively developed, the system as a whole. So again, this is not an on-demand water heating type of situation. So we would want to just size the system as a whole for the peak heating draw, and we want to make sure that we're going to be storing enough hot water for your peak draw throughout the day. I have a couple slides after this that showcase how we're going to be doing that, but in terms of how we would size backup, that's a question that I just need to do with my own personal deep dive into a little bit more. All right, so here is a system schematic for a 3-sensor temperature control. So what we're looking at here, and remember the QAHV is a self-contained unit, so everything, all the water, all the piping that we're seeing here is all water piping, so no refrigerant piping external to the unit. So we're going to be producing this hot water in the unit itself and sending it to a hermetic type storage tank. Now, in this particular example, we have up to 3 thermistors in one storage tank, so that way we can detect and see the stratification of the water in the water tank. So the typical primary storage tank feeds to a temperature maintenance storage tank. That's what we're talking about for this particular scenario. So, and just to showcase a little bit further, in this example, we have multiple sinks, a shower system as well. So this is for an entire building's hot water demands, is what we're looking at here. Within the QAHV itself, within the condense unit, this is going to be utilizing a brand new patented twisted and spiral gas cooler. So the 3 connected refrigerant pipes are wound around the twisted water pipe, maximizing the surface area for heat transfer. The continuous spiral grooves in the twisted pipe accelerates the turbulence effect of the water and also helps to reduce the pressure loss within the heat exchanger, ultimately contributing to an enhanced efficiency. Now, this, coupled with an inverter scroll compressor within the VRF system, the QAHV is capable of significantly increasing the annual efficiency when compared especially to fixed speed systems that are simple on-off. So we have 3 different methods that we could use to control the water temperature in a QAHV. We have a local control option. This is not recommended, but this is controlling to the target outlet water temperature of the QAHV. I say we don't recommend this because we want to ultimately be designing the QAHV for maintaining an adequate amount of water in storage tanks. So we have the 3 sensor control, which is what we saw in the previous schematic, utilizing 3 separate water temperatures. But we also have a 6 sensor control option, where that's when we're twinning together multiple of the condense units. And by using 6 different water temperatures, we're going to have a lot more precise control and cycling on and off of the QAHV as needed, as demand is calling for. So just showcasing the different methods with which we can control. Here's for the local control, targeting to the outlet water temperature for this instance, which is feeding into a semi-hermetic storage tank. We have the 3 sensor control. This is similar to what we just saw previously. Just the temperature sensors are located at the top, middle, and bottom of the unit. Just based on gravity within the unit itself, we're going to be getting 3 separate temperature readings. It's going to be hotter water towards the top of the tank, colder water towards the bottom. But from an actual control logic standpoint, this is what we're going to be looking at in the system. So ultimately, nighttime is when the QAHV is going to be doing the bulk of its supply of hot water to the storage tank. So in this particular instance, on the top left here, we have the trigger to turn on the QAHV when the middle temperature sensor drops below a specific set point. That way we know that we have less than 50% of our tank is achieving our minimum set point temperature within the hot water tank. At that point, the QAHV will turn on, and it will turn on until the furthest, the temperature sensor to the furthest to the bottom, that achieves the setting temperature necessary, in which case the heat pump will turn off. So when all 3 temperature sensors are registering water temperature above the setting temp, that's when we know the whole storage tank is at appropriate volume or appropriate temperature. For daytime operation, works a little bit differently. So again, the bulk of the hot water heating is going to be done in an unoccupied state. We want to just get all the hot water we need and maintain the temperature of the hot water in the tank. So for daytime operation, we're not going to be cycling the QAHV on until the topmost water temperature sensor dips below that setting temp. And we're going to run that system until the middle water temperature sensor achieves that setting temp, and at which point the QAHV will turn off. And the reason we're operating like this is because if we're trying to get that TH17, that bottommost water temp sensor, to constantly be at the minimum setting temp. The QAHV is just going to be cycling on all day, and it's not going to be operating in its most efficient state. Most efficiently, this is going to be maintaining an appropriate amount of water in these tanks. It's not going to be utilized as an on-demand heating. We're just going to make sure we have enough hot water on hand. And just one more slide on this topic. This is the 6 sensor control, just demonstrating how we have a little bit more precise control by incorporating an additional 3 sensors. This is when you twin together multiple storage tanks. You have multiple QAHV units that are manifolded together. And by having up to 6 different sensor controls, this is how you're going to get more precise control. We'll know a little bit more on an on-demand basis when we need to turn the unit on, when we need to turn off, when we need more hot water. So ultimately, this just rounds out the last of the control methods for the QAHV domestic hot water heat pump. And with that, that actually sums up the information I have for this evening. I know that there was a lot of time there, so if anyone have any questions, please feel free to let me know. Anything that I'm not able to answer now, I will certainly write it down. I'll get it to our applications group, and I could get a message out to the group afterwards. So thank you very much, everybody, and if you have any questions, I'll be happy to take them.
I've got a question about the HEX system that you guys have going right now. You say they're what, 3 or 6 ton units?
That's correct. Yep.
How many, I guess, branches can you have coming off of that? You know, so we're seeing a lot of like these passive houses that have really low loads, you know, half-ton loads. So what can? So
Hi, Hazel.
Your boss there.
Sorry, I'm dealing with some technical difficulties. So if you have a 3 ton unit, can you do like multiple like half-ton, you know, spaces that require a half-ton each?
Yeah, certainly. I'd imagine so. So like, well, the issue with that is we're not going to be able to provide precise temperature control to each of those spaces. Again, because the HEX unit is going to be feeding into that buffer tank, and the buffer tank is ultimately what's going to be sending the hot water throughout. So if we have multiple half-ton spaces all on one loop that add up to 3 tons, if we have 6 half-ton spaces all being served by one HEX unit, that is something that we certainly could work with, yeah.
Okay.
Stop you, Isaiah.
Isaiah,
Talking again?
he's talking again, but we'll just talk over him. It sounds
Okay,
like you would have that buffer tank would serve a manifold, and then you'd have home runs to that manifold with mixing valves that are controlled by your terminal devices.
Trying to see if I have a slide on. Give me one second, so no one needs to watch me go through that. I think I have an application that actually demonstrates exactly that. Yes. So as in this particular, yes. So that for this particular loop, we have 2 separate 6-ton hexes. They're going to be twinned together, feeding into one single buffer tank. The buffer tank, again, is going to be going around. In this particular example, it's done in tandem with the modulating gas-fired boiler, but ultimately it's going to be served into multiple different zone headers. So exactly as you said, yeah, that's how we would deliver that to multiple zones.
Correct me if I'm wrong, Mike, but I think the HEX is allowing an outdoor unit to take over the function of a boiler.
Yes, that is correct. Yeah, so forgive me. So this last slide, this is how we would, like the snow melt radiant floor tube with the boiler. This slide, I don't even know why I have the previous one in there. This is done where it eliminates the gas-fired boiler. So this one is entirely done with a HEX unit with no backup boiler present.
Right. So if we wanted to electrify tomorrow, this is what we do.
If you want to electrify tomorrow, certainly I'd say that this is what we're going to be looking at. Obviously, I'm excited about the HVRF. I'm excited about QAHV. Unfortunately, they're not. We're not stocking them right now. We're not designing around them right now at this point. If you do have any HVRF or QAHV projects in the pipeline, depending on their ship dates and depending on when we're ultimately going to be seeing them go out, we could work with you and develop a design around that. But yeah, especially with the QAHV, we're looking at Q4 2021. Any like spring 2021, I don't even want to touch that because the last thing I want to hear is, hey, we have a 2-month delay. And I'm like, all right, well, you need to redesign your entire project. Go back to the drawing board, and I've wiped my hands clean of the problem. That's the last thing I want to do.
And
Mike,
I guess the question there. Go ahead.
Sorry,
I've been talking a lot to you,
Anthony, the blank square here, or rectangle. Yeah, I wanted to chime in regarding the buffer tank. Why is that required on this system?
So the buffer tanks are going to be required just in the event that the defrost cycle it goes long enough and in a cold enough ambient day that the water within the HEX unit system, we're ultimately going to be running into a shortage of the hot water necessary. So we're going to be having a lag time, especially on delivering hot water to spaces that are calling for it if we don't have that buffer tank. So it pretty much, you would be forced to go into like an on-demand hot water heating mode at that point. And the HEX units, they're not quite designed for that. They're almost there. Let's put it like that. So with that said, we're going to require that for each HEX loop.
Gotcha. But you guys have HEX now, and I did a project a while back where we did radiant floors, and I don't remember having a buffer tank.
No, so if that's I can't speak one way or the other. Maybe this is a recent revision.
Yeah, no, I mean it may be a little bit different now, and it's possible that we left that out and should have included it. I haven't heard anything from that project. It was a long time ago, probably like over 5 years ago.
Well,
but
I'm happy to hear that everything's working.
Yeah.
But I do know that a lot of what we know about the HEX unit's capabilities have been redeveloped, and the application note is one of the newer ones that have been revised to include that. So I think that may just be as a result of exactly as I said before. There's a significant lag time between calling for heating and heating being available.
Yeah, and I mean on that project, that the flooring was just like an absolute supplemental comfort type thing. We had VRF above, so that's probably why they never like felt any problem.
Exactly. Yeah.
Like, does the volume of the water in that loop make any difference to whether you need a buffer tank or not? Like if you have a big loop going out to the building.
So I'm going purely off of the application now and the design criteria. And the design criteria, that's just one of the components that is required in the system. So I can't really say one way or another whether or not the volume of the water is going to either diminish the necessity to that or not. But just thinking out loud, I think that may play a factor. And I think as a result, the buffer tank was just done as a flat required across all different system sizes.
Okay.
Question, Mike. You have the HEX. Yeah. Oh, I got a lot.
Here we go.
So the HEX, you've shown that always fed by a branch controller. Could it be fed directly by an outdoor unit?
Yes, it can. Yes, it can. We could have a one-to-one only for however, the booster units need to be on a heat recovery system.
Okay.
So if you had just thinking hypothetically here, if you had, what's that, Ken?
Just reiterating what you said, the booster needs to be on basically off a branch controller.
That's correct.
And be directly connected to an outdoor unit.
Mm-hmm.
I yield.
So I suppose, like, if you had the outdoor unit, you had like a 20-ton outdoor unit, if you didn't have a branch controller, how would you connect it to multiple HEX units? Is that why you need the branch controller besides the heat recovery between the HEX units themselves?
That's a good question. I'm not. That was one of those where I just read that note that it must be attached to heat recovery. Let me read up as to the rationale behind that.
Yeah, are these different than the former HEX units, Mike? Because they are.
I'm sorry. Go ahead.
I was because I believe that, like, in the old system, and again, like, I'm going back probably like 2014 to when I was working on this project, but where I had a HEX, because I haven't really used it since, I don't think, but we didn't have a heat recovery system on that, and I do believe that we were using like the Y series, I guess, equipment, and I think there was something that said like you could only use like one hex on your system or something like that. I think it was something that in the past it was written like that. But again, we didn't have a heat recovery system, so we only had the heat pump system on it.
Yeah, so I'm looking at the application note right now. Actually, I can bring this on over here. I'll show everybody. So this is what I'm. Second. So in terms of VRF system integration, just reading off the page here. The HEX and booster unit are connected to the VRF system just as any other indoor fan coil unit. The HEX and booster units both can be integrated with the City Multi R2 heat recovery system. However, only the HEX unit, that's the HEX auxiliary unit, can be connected to the Y series equipment. Just breaking down that the flexibility on the HEX auxiliary units, that can be connected to pretty much any three-phase equipment as opposed to the booster unit, just simply R2 equipment only. So as to whether or not the units themselves have changed, I can look into that. Not entirely certain why that may have changed at this point, but yeah, let me dig into the rationale behind that.
I have a question there about the domestic hot water, which I know you mentioned you have to research some of this. But if they're not instantaneous and they're going to need to store domestic, hot water for the system to operate, why is it during the day that we're only storing, say, half or 2/3 of the quantity of water, controlling it by the middle and upper sensor? It seems like with a system like that, you're going to want to run constantly and at a slow rate, and just keep on building for 24 hours and build it for the capacity of the actual tanks, so that you don't run out during the 24-hour period.
Gotcha. Yeah. So my understanding of that, it comes down to the fact that if the daytime it was controlled to a similar control method to the nighttime, where we want all three sensors to be satisfying the temperature requirement, is that would potentially run into circumstances where the QAHV was just always on. So whenever any hot water was used throughout a system during the daytime, during a common hot water usage time, you're not going to get the efficiency gains that you're looking for with an electric heat pump, just having it to be always on as opposed to maintaining a mostly high temperature water capacity within that storage tank. But that said, that's a great question. I want to dig into that more because I didn't see any further rationale to that. So I got that one written down.
Seems like in a heating climate, you would almost want that operating more during the day when it's a little more efficient. But
yeah, I see that thinking, and I don't necessarily disagree with you. I'm just yeah. So sure. Let me dig into that, and I'll ask that same question. I think it's a great question.
Any other questions there for Mike?
Okay, back to me. Wanted to make sure other people get a chance.
Ken, nobody wants to hear you talk.
I do. Can you explain about how we get increased heating capacity with the HVRF? And that really caught my interest because we've been working with an engineer who is concerned about HVRF not having the same supply air temperature on the fan coil unit as if we just had a refrigerant all the way to the fan coil. So could you comment on that?
Are you referring to the increases in the sensible heating capacity specifically?
Yeah.
Okay, so fortunately, that's a question I have to forward along as well because that's one that has jarred my mind the same way. I was just like, how are we seeing that? Let me dig into that, and that'll be a question that I'll send out in response along with all these others to the group.
All right, cool. Thanks. I was really interested to see that because that would be good news. I just want to have some understanding of why it's that way.
Sure, gotcha.
Yeah, Mike, you said that there's a limitation only on the domestic water side for temperature out. I mean, of course, there's a limitation on the heating side. You can't get like 1,000 degrees or something. But I think you were saying that there was like the max temperature is 194.
Yeah. So the European model, their engineering data book has the hot water temperatures being able to boost up to 194. My understanding is that UL testing for domestic hot water equipment, for the types of applications that the QAHV will be serving, it is only like they have limitations on the high end of what the water temperature could be. Again, I am certainly entering a territory that I'm not entirely familiar with, so I'm kind of just regurgitating information that I've been force-fed on this topic. So I'll read into that a little bit more as to what the rationale behind that and what that the estimated hot water temperatures are going to be looking like.
Gotcha. Yeah, I mean that makes sense that domestic would be limited, for scalding purposes.
Yeah, exactly.
But yeah, I don't think that I caught that was Ken's question, I guess, was there was an engineer that he's working with that is skeptical, I guess, about the HVRF not being able to get the same hot air out of the unit as the direct expansion unit. And I don't think that I caught that portion of the presentation where you mentioned the reverse of that. Did you mention that the HVRF can get higher temperatures? Is that what you said?
No. So specifically, So specifically, and again, this is one of those copy-pasted details, so I just got to dig into the rationale why. We're estimating that we're going to be able to get up to 10% of sensible heating capacity increases with the HVRF just by using the water as the fluid as opposed to refrigerant. Got to dig into the rationale why. I'm not entirely sure yet. I'm fortunately the Berklee College of Music install that we have, as we had pointed out, actually has BTU meters throughout the entire system. So once we get, I think we need to wait to ultimately for all the students to come back to the schools, which I don't believe is going to be until next semester. At that point, then we're going to potentially be able to get all the raw data for it, get an analysis, and hopefully I imagine by the end of next year, I know it's a hell of a timeline, but it's what we're dealing with here, especially in COVID times. But by the end of the next year, we can certainly have a very detailed case study, really detailing a like-for-like comparison between heating and cooling capacities.
Gotcha. And on these ducted units, are the coils being modified for hot water? Is that part of it?
Yes. So because all of the valves in the system are no longer going to be sending refrigerant from the BC to the fan coil for the LEV in the fan coil to have the expansion process of the refrigerant, we're eliminating that from the coil itself. Essentially, all the fan coils need to be reconfigured to essentially be like chilled and hot water coils. So we're repurposing each one individually, and because of that, the only ones that we have capabilities off the bat are the medium static pressure concealed ducted units. With that said, let me just pull up these pictures. Yeah, with that said, I just stopped sharing the screen. The Berklee College of Music, we have a mixture of both cassettes and concealed ducted units. The cassettes were actually ordered directly from Europe, as opposed to having to go and reconfigure themselves, just as a method with multiple ducted and ductless units. But right off the bat, we're only going to be looking at concealed medium static pressure ducted units.
Gotcha. And I guess is this thinking of the efficiency of the system, having the piping in there? I don't want to say that the piping is similar to ductwork, but how does this impact the Energy Star certifications and such?
That's a great question, and that's a question for Matt Berry. That's for my boss, because he's going through that whole process himself. So let me ask about how that's going to affect that.
All right. Sorry, Ken, I cut in. Sorry.
You don't need to apologize to Ken. He's got like 17 more of these for me.
Back to you, Ken.